Let's get started. So, just as a quick recap from last time, we were covering logistic regression. And so we're going to pick off with one last bit with our regular logistic regression, and then we'll move on to thinking about outcomes with multiple discrete outcomes, so multinomial logistic regression. So before I dive in, does anyone have any questions or concerns about that? Nope. Okay. Let's jump into this. Okay, hang on. There we go. All right. So, one thing that is slightly different about the logistic regression that I had mentioned is that unlike with the linear regression, right, where we have maybe a plot that looks like this, and I have my points, and then we have a line that goes through these, right? The procedure that we use to figure out that this is the best line, right, is that we minimize these distances, right, from our actual points to our fitted line. But now we are dealing with something slightly different, right? We're talking about something with these discrete values. You know, we might set them at 0 and at 1, and then you have a bunch of data points that look something like this, right? And so, sort of visually speaking, there's not this sort of analogous necessarily way of drawing this line, right? And in fact, we know, right, from last time that you're actually generating this S-shaped probability curve. So this uses a slightly different estimation method using what's called a likelihood. And the basic idea behind this is essentially something like this. If I have a bunch of data points that maybe are on this line here, with a likelihood function, you're assuming that there's some kind of probability distribution that covers these points, right? And so in a similar way to how we tried to draw a bunch of different lines through all the points, here I can draw a bunch of sort of probability distributions. Okay, maybe my probability distribution looks like this. Maybe it looks like this. Or maybe it looks like this. Or maybe it looks like this. Okay, and so given these points, raise your hand if you think the blue line looks like the best distribution to represent this spread of points. Anyone? Or how about the yellow line? The red line? Okay, a bunch of people. Green line, right? So this is in the same way where we tried to draw a bunch of lines through all the points. The likelihood estimator is essentially trying to figure out, okay, if I were to have some kind of probability distribution, which distribution would most likely essentially cover the points, like having those points be a part of that distribution. You can see that, you know, because these are distributions, like even on the blue one, right, technically speaking, all of these x's could be part of the blue distribution. It's just very, very unlikely, right? And so the idea is with this particular set that we're looking at, a distribution is defined by, actually, does anyone know what a distribution is defined by? What is a normal distribution defined by? Yeah, mean and standard deviation. Okay, so a distribution is defined by a set of parameters, right? So if I had like a uniform distribution, the two parameters are your min value and your max value. If you had a normal distribution, the parameters are your mean and your standard deviation. And so what you can do is that you can see what values of the parameters, the mean and your standard deviation, need to take on in order to maximize the likelihood that the distribution being described by those parameters capture those points. Okay? And I'll write really quickly the equation that corresponds to the logistic regression when we're thinking about maximizing the likelihood. But that's just to give you a sense of what's happening behind the scenes. This is really the conceptual framework for what the likelihood is trying to do. Okay. So it uses a log likelihood function. So this is describing the plausibility of a model parameter value given specific observed data. And that is going to look like this. Likelihood, which is a function of beta naught and beta, is equal to something like this. And if you remember, the probability is that portion of the logistic that looks something like this. Negative log 1 plus e to the beta naught plus beta x I. Okay, and to solve for the betas, essentially you set your partial derivatives equal to 0 and approximate numerically. Which means, unlike the linear regression, this doesn't have a solved analytical solution, our xtx inverse times xty. The maximum likelihood estimator always approximates our betas numerically instead of analytically. Okay, and so this is the equation for the likelihood function that you are trying to maximize, but again, this is just the thing that's kind of happening behind the scenes. You don't need to run these manually unless you're taking in statistics or econometrics class. Okay. So again, to re-emphasize, it's really this kind of thing, right? And as an analogy for the straight lines that go through all the points in our linear regression, this is kind of what's happening as we think about distributions of outcomes as it relates to these binary or categorical outcomes. Yes?
So the log likelihood function, it gives you, maybe this is not the right way to say it, so I'm thinking about that, is like the confidence interval of a value for a particular parameter, right? So it'll tell you that it's, is it like would it be right to say it's 60% likely that this is a good value, or what's the right way to like
No.
describe it?
So, okay. So I'll talk about it kind of conceptually really quick. If this red distribution represents a distribution function related to these values, you might say that this point, that there is some probability that you get this point amongst all of the points in the distribution. So this is some number, but then would you say that this number representing that probability of taking that value in this distribution is bigger or smaller than if it was coming from the blue distribution?
It'll be bigger because it sits in the meaty part of the bell curve.
Yes.
Yeah.
So that's the essential concept. This is a bigger sort of probability. And so you want the sort of probabilities or likelihoods. They're actually kind of interchangeable, although one is talking about I think the difference when we say likelihood or probability is in reference to like data from the distribution versus probability, the parameter values generating it. But yeah, they're often used interchangeably. So okay, so you want that number that you're thinking about, the likelihood or the probability that that's coming from the red to be as high as possible, right? And so that's what we're talking about when you want the likelihood to be as high as possible.
Okay. And that can change based on model, right? So you can have different models, model 1, 2, 3, 4 for specific data. You may have different log likelihood values
Yes.
for the parameters within that model, right?
Yeah. So, just to be clear, the likelihood is kind of like a reference value, is not directly telling you anything about the parameters in the same way that when we think about a linear regression, like we are minimizing the sum of the squared errors. That's kind of like what this likelihood function is doing. You are maximizing the likelihood, and you're doing that by figuring out the best betas to do that. In the linear regression, the analogy would be you are minimizing the sum of squared errors, and you are figuring out the best betas to do that. Okay. Cool. Any other questions? Okay. So let's move on to talking about the next sort of evolution for logistic regression is multinomial logistic regression. So this is a generalization of logistic regression to multi-class problems. So, if our binary outcome looks something like this, f ki, this is our outcome and observations. Then for multiple outcomes, we'll have something like this. Oh, let me actually do it in a vectorized notation. So now k can be greater than 2. And you have different set of betas for each outcome. Okay? So this idea that we had looked at from before, where you had our example of what was it? Democrat wins. So it's percent Democrats, and then Democrat win probability, right? And so we had something that looked like this. And the idea is, sort of generically speaking, we are now thinking about situations where you may have multiple outcomes. Right? And remember that the sum of all of these at any time have to be equal to 1. So now you could have like a P of X, P of Y, P of Z. Okay. Probably easiest to digest this with an example, so we'll jump into that now, unless anyone has any questions about this. Yeah.
So are X, Y, Z the predictors of these 3 outcomes then? They come on the horizontal axis? Or is it 3 different probabilities all determined by values on the x-axis?
Yeah, so importantly, these are your probabilities associated with the different outcomes in your response variable, in your y. And so it could be, if I were to do this simplistically, in our previous example, this is the percent of Democrats in a region, and then this is the probability that a Democrat wins. And you could have a data set that contains if a Democrat wins, a Republican wins, or an independent wins, and then you would have 3 different outcomes, right?
All determined by the percentage of Democrats
Yes.
in that region.
Yeah. You can get more complicated with more X variables, right? But then you start to run into the same sort of visualization issues as with the linear regression. In smaller models, like one thing you could do is keep, if you have x1 and x2, you keep x2 fixed to its average value and then vary across x1, and then keep x1 fixed and then vary across x2 and see what happens to the probabilities, and it gives you at least some sense of how the outcomes are affected by your variable. Yeah.
So the example you just gave, you could basically have, you have three outcomes, and you just say one outcome stays fixed. So let's take the independent. We always say no matter what they get.
No.
No.
The outcomes are what you're visualizing here. I'm talking about if I had x1 and x2. If you had 2 explanatory variables, you could fix one, because otherwise you would display this in a 3rd dimension on a z-axis, and then you'd have contours of probabilities, which already probably gets a little confusing. Yes. Okay. Okay, so let's look at an example in RStudio. Okay, so I have uploaded a data set into lecture 11 on campus. So if you want to follow along, go ahead and grab that. And we are going to load in a bunch of libraries.
This is the Disney data set, right?
Yes. Okay, so we've got all of these. Oh, apparently I don't have PLS installed. All right. So load all these guys up. And I will have a data set called Disney, which we can take a quick look at. I'll do it down here so that we don't lose all the code. Okay. So it's got 8 columns. And here you can see the name of, so this data set is a data set of Disney plus movies and TV shows. I think it's like 2 years old at this point, so it's not going to have a lot of the newer stuff. But title, name of the TV or movie, year that it came out, or range of years for TV shows. Certificate gives the rating, right? It's got both movie ratings and TV ratings. Runtime is the length in minutes. Genre, so we've got a bunch of different genres. Let's see. And you can actually see that for the genres, it can have multiple categories. Ratings, I believe that is the average rating that it has on the show, the number of votes that determine those ratings, and then the top director or star associated with that title. Okay. What we're gonna do, let's do a quick visualization of pieces of this that we're interested in. And so we're actually gonna see, we're going to attempt to see how the certificate, in other words, if it's PG, PG-13, R, TV mature, whatever, is related to or can be explained by other attributes of the show. Okay. So let's do this. And I'm actually going to I'm actually going to filter this out just for movies. So we're only going to look at a subset of the data that contains these ratings, which are specifically movie ratings. We are also going to filter this data set to only include movies that are less than about 3.5 hours long, because ain't nobody got time to watch super long movies. And we're gonna look at ratings at movies that had a rating above 3. Some of this is a little bit artificial just to kind of make the example work, but that's all right. Hopefully everyone will still understand what's going on here. Okay, so we're gonna make this. Oh, I've got some kind of mistake. Nope, it went away. Oh, I think I need to put in another package really quick. Our color brewer lets you use more interesting palettes in your plots. So what we're gonna do, if you're following along, is along the x-axis, it's going to be how long the movie is, and on the y-axis is gonna say how highly rated the movie is. And then the colors are going to indicate the certificate. So x-axis, movie runtime in minutes. Y-axis will be voted rating. And that should be it. Oh.
Which should be runtime underscore min in the first line.
Yep. Thank you. Okay.
What is scale color brewer?
Scale color brewer.
14, yeah. What is it? Is that like a...
That, so, okay. Let me show you. So if I take this out, it's a different palette. That's all. I just prefer this palette.
Oh, it's just a palette.
Yeah.
Oh, okay. Then that can be used for all elements of GG plot. It's not specific to.
Yes. Okay, someone remind me, how do I pop this out again? Zoom? I thought I just did that. No. Oh, it's on my other screen. I was like, okay, here we go. Okay. So the general idea here is whether or not there is some kind of like correlation between our runtime and voted ratings that we can help to separate these points out, right? And so maybe a little bit harder to say, but maybe a little bit more red dots here on lower run times. So G-rated movies, which kind of makes sense, and then blue or green maybe out here. PG-13 movies tend to be a little bit longer, and so we'll see if that's something that comes out of the modeling when we run it. Okay. So let's make our subset really quickly. And that's just going to be this data here. So I'm just going to copy and paste that. And we will create our model. So regressing certificate on runtime and rating, and our data is Disney filtered. So when you run this, you're going to get a little message here. Gives initial value, iteration, final value converged. So these are indicators for the actual running of the model. And as I mentioned before, this is with logistic regressions, we're running numerically. And so that's why there is this iterative thing that's going on. Summary, MNL fit. And what you see here are coefficients specific to each of your outcomes and the standard errors associated with those coefficients, right? Okay. So as I had mentioned last time, well, one more thing. Notice that there is one coefficient that's missing. And so what is that? Or one set of coefficients. Yeah, for the G rating.
Is that the base level?
Yes, it is the base level, and the reason why it is omitted, right, is because with this information, this is the information that you would use to construct a probability curve, right? And if I have 4 outcomes and 3 probability curves, I should be able to determine the probability curve of the last one, right? Because it's always sums up to 1, okay? Okay, so there is an effects package. Okay, 1 second. I don't know why this wasn't included. One more package. Nope. Or is it? There we go. Lowercase e. So this is a handy package that will let us do some interesting plotting. So essentially what this does is I can take using this function from the package effect, I can look at individual explanatory variables and plug it into the model. And if we take a look at what gets spit out, what it does is it looks across the range of values. So if we look at rating, we have going down from essentially 3 up to 9. So it'll spit out a range of values and then look at the probabilities of outcomes associated with those values. Okay, so this is, in essence, drawing out that probability curve for us. Okay, and it's doing it via our logistic regression equation that we had from last time, right? With the exponentiated betas. So a quick refresher. Oh, well, I can't draw it on here with this, but all right, let me just pull it up really quick. So just a quick refresher. The probability of your outcome. Actually, does anyone remember what it is? So it's exp beta naught plus beta x divided by 1 plus exp. Oop. So this equation is slightly different in a multinomial setting. But essentially, the effects package is doing this work for you, plugging in the betas and calculating the probabilities. Okay. But wait, you say, what is missing here? How can I calculate the probabilities given only varying my ratings? What other information do I need?
Runtime?
Yes, exactly. So this runtime, right, if I have y equals beta x1 plus beta x2, I can't predict y with only x1. You also need x2, but essentially we've basically said only vary the rating. And so when you do this, what the effect function is doing is that it is holding your runtime fixed to the average runtime. So then it's generating a probability plot, right? But only at a certain specific runtime. Yes.
Can you vary the function to not take the average in some arbitrary runtime that you want? So you want to know, let's say, movies that run like, I don't know, 120 minutes?
Yes. Yeah, you can do that. There's a setting, I don't know it off the top of my head, but in effect where you can fix other values of x.
Okay.
Yeah. But so I can also do this for runtime. Oop. And it will hold rating fixed. So I'm going to copy and paste some code here. Okay, don't need to follow along for this part. I'm just gonna make 2 plots. There is a custom function that I've made that can extract information from that effect object that I generated that I can then use for plotting. Oop, need to run this first. No, uh-oh. This is new. All right, 1 second. Did I not run these? Well, we'll see if that still works. Yeah, okay, cool. Okay, so this is a plot across the range of ratings. This is they split it up into 5 points, so it's 1 through 5, but really it's ratings 4 through 9 or whatever the numbers were. Okay, so given the average runtime, the probability that the movie is G rated is like 30%. At the average length of all of those movies. The probability that it's PG is like 50%. The probability that it's PG-13, when at the lowest rating, is like a little bit above 10%, and the probability that it's R is a little bit below 10%, right? And then these change as the ratings increase. Yeah.
The shaded region is the confidence interval,
Yes.
and if it overlaps, means that there's no statistically significant difference in the probability of, let's say, a movie that's rated 1 to lie either in R or PG-13, because the two intervals overlap, the green and the purple one.
Kind of. So these are 95% confidence intervals.
Yeah.
So then, really, if you're talking about the difference, it would be whenever the confidence interval overlaps with the average, with the actual line, right? And so here, right here, where the blue confidence interval intersects the green mean line is when you say it's like within a 95% confidence
So if
difference.
just the shaded regions overlap, does that not mean that the two could be essentially similar, have let's say similar probability of?
No, I mean they are, but you're like interpreting it in a, it's like the 95th percentiles overlapping with the 95th percentile. That's not really an indication of statistical significance or anything like that, right?
But if the lines intersect, essentially would that mean that there's no statistically significant difference?
No, if the lines intersect wouldn't mean that for that point it wouldn't matter.
The probability would be the same, so I'm
But
saying,
it wouldn't matter what
how do
the
you say
rating
that
would be.
how do you say that the probability is different at any given rating for a movie to be in one of the categories?
So if they overlap, let's say a PG-13 and an R movie overlap, the average runtime overlaps, then they have the same probability of that given rating, right? At that point.
I don't think we had function on that.
It's the average runtime, isn't it?
The runtime was fixed.
No, the line is the average runtime.
Okay. The point at which two of the intervals overlap or like touch each other, you are saying that 2.5% of the time and 2.5% of the time, so it's 2.5% squared, that they would be the same.
Yeah.
So the chances that they are actually so the chances that, okay, what's 25 times 25? Anyone? 625. Okay. So that would be, if I'm not right? 0.00625. Or 0.9 9375. So the point at which they meet, I think this is the right interpretation. You were saying that 0.6% of the time that they would not be statistically different, and 99.325% of the time they would be different.
Okay.
I think that's the right interpretation.
And the point where the line intersects, essentially, where does that lie?
That's right here, right?
Oh, okay. Yeah. Okay.
Because they're 95% confidence intervals.
They're saying, yeah.
Okay. Good? So them intersecting doesn't really tell you anything about statistically different or, I mean, yeah, you can work out the probabilities. But okay, anyways, the bigger takeaway of this plot, right, is that the ratings given a specific runtime has probabilities associated with outcomes that look something like this. If you were trying to do a prediction, let's say, okay, let me just pull out the actual number. Mean Disney dot filter dollar runtime min. Okay, 88 minutes. So these, okay, again, these ratings correspond to 4, 5, 6, 7, 8, I think. Is that right? Sorry, 1 second. 4, 5, 6, 8, 9. It's jumping around a little bit. It does it by quantiles. So, if I were to pose this question to you guys, at 88 minutes and a rating of 4, what probability, or what is the rating that you would guess for a movie? So, if this was 4 and at 88 minutes, what would you guess? Sorry? PG, yes. It has the highest probability. Okay, what about at a rating of 5 and 88 minutes? Still PG, right? It has the highest probability, and so on and so forth. Right up until your rating is like 9. It doesn't cross over until right at the end here, right? So I would guess PG-13 right at the end. Okay, so this helps you kind of map out an outcome. And then let's look at that was rating, so let's look at runtime. So here, our average rating is 6.7. Okay, so this represents the probability plot for our different outcomes across a range of runtimes with an average rating of 6.7. Okay. So if the movie's really short, so on this side, at this 6.7 rating, what would you guys, if you had to choose, what would the rating be? G, right? Because it's red. Red is the highest probability. Okay, if the movie's really long, we would choose PG-13. It's green. And then if it's kind of middling, then it's probably PG. And one of the interesting things to note is that R never is the dominant probability in either this one or the other one. And maybe it will be if you go across ranges, right? But at least in the two that we've seen, it isn't. Yeah.
None of these graphs tell us that when the lines were to, maybe it's not this one specifically, but like when the lines overlap, the averages overlap, it would say at this runtime for the rating of 6.7, like it didn't, what I'm doing is like, is how would we show, it doesn't matter whether it's rated as G or PG, PG-13 or R for a given runtime. Like if I looked at PG and G at, you know, right where they intersect, right? At the probability of like 38, right? Whatever.
Yeah.
I don't think this graph shows it, but there isn't a graph that would say at that point they intersect. It doesn't matter if to rate it G or PG because you're gonna get the same rating. But as an example, like if we did if we flipped it, or like ratings were.
I don't know what you're saying.
I'm
Do you have a question?
Yeah, my question is, how would I do this graph or figure, say I'm a movie executive, and I want to know, well, is there any difference in me rating this movie G or PG as with respect to rating? So if I have a movie that's 85 minutes, and I want to get the highest rating, how would I know to rate it G or PG?
No, you're thinking about this backwards.
Okay.
The way we're treating this is that the certificate is a function of the rating and the runtime, not the other way around. Make sense?
Yeah, well, we could do what I'm suggesting, right? We could flip it and show
But that would
something.
be, well, I mean, no, normally, okay, you can't just swap your X's and Y's.
Oh no, I'm not saying just swap them. I'm saying that we could compute what I'm like, to figure out the answer to what
I don't know what you were asking.
I'm asking for a given runtime, or I'm a movie executive.
Okay, so
and I have five,
you fix a runtime,
yeah.
which means now I have a set, this would be going back to the last one. You now have a set of probabilities related to the rating of a movie.
Right, yeah.
Yes.
Yeah, that's okay. That's where I'm at. Yes. So you could, if you did
So, okay, so think of it this way.
ratings on the
This is a plot where you've fixed the rating. If you fix the runtime to some arbitrary number, it could be, it's a different number than the average, which we looked at. You would generate another plot, and that plot would look probably similar, but a little bit different to our previous plot.
Right.
Okay.
Yes.
So, if we were to replot this at a runtime of 40 minutes instead of, what did I say, 88 minutes, then, maybe the red line would be higher, right? Because we do know that, like, shorter runtime would be more favoring the G-rated movies, right? So maybe this goes up, maybe the blue line goes down a little bit, maybe the R goes down, maybe the green goes, I don't know, right? So these lines would all shift in some way. Okay.
If the shift is minor, as you change that average fixed number, would it be useful to just plot all runtimes into one using the shaded region? So all places the blue line could be at different runtimes.
Yeah, I mean, you can visualize this in many ways. Yeah.
So you could change the function to, instead of plotting the shader as confidence intervals, you could say that every time position of the line at different runtimes.
Yeah, I mean, you can plot this however you have the data to visualize something, right? So.
Oh, I just wondered the value along the x-axis. Did you set up in that way, or just integrate from 1 to 5?
It's always 1 to 5 it's a issue with the effects function, but it breaks it down into 5 values, 5.
Represents this matrix.
Yeah, it gives the 20th percentile, 40th percentile,
Oh.
60th percentile, 80th percentile. So this is first, second, third, fourth, fifth, and then the values that these correspond to is like, you can look it up. But basically I'm saying low rating to high rating. So don't worry about the 1 to 5. Yeah. And same with the runtime. Okay, so what we're gonna do now is what I was kind of hinting at with plugging in different values to see what the model would predict. So this line 60 that I just wrote is going to systematically look at a range of runtimes and ratings, okay? And so we're going to predict based off of that range of values. Okay, so I'm going to jump up really quick just to refresh our memories here. I'll go back down so everyone can see the code. Okay. So this is what we observe in reality, but I could point to like a specific area in this plot, right? I could say, okay, if you had a 50-minute runtime and you had a rating of 5.5, what would the model predict as the outcome? Okay. And so what would the model tell us? What information would the model give us about, from what we've seen so far in the MNL? Yeah, so it would give probability values, right? It would say, at this point, right, based on those probability curves that I drew, if I just identified that exact point, it would say, G-rated movie has a 50% chance, and a PG movie has like a 20% chance, blah, blah, blah. Or it has that probability of being that particular outcome. So in fact, I could map this entire region based off of my model and predict outcomes based on what the highest probability outcome is for any given point along this map, right? And so that's what I'm doing here. These give the predictions. And I can go ahead and plot that. So geom point Actually, all right, I'm going to copy and paste this so that we can
What is
speed this along.
backward slash n predicted backward slash n real?
Yeah,
Does
so
anyone-
I'll break this down in a second. Okay. And you guys can, this will be posted online. Okay. So, there it is. So, I've basically pointed at every single possible combination, or not every single, but I looked at a bunch of combinations of movie runtimes and ratings, done the prediction in the model to figure out the probabilities, and then you assign the highest probability as your prediction, and this is the map that gets shown, okay? And so, note that of the 4 outcomes, if you remember, we were saying that the R-rated movies never get predicted, or weren't being shown as the highest probability in any event. And we can see that reflected here, right? There's no purple in this plot. And as your rating increases, you tend to have more, okay, hang on. So if I just go from bottom to top, both my red and my green increase in amount, and so typically the higher rated the movie is, the less likely that it is to be a PG movie. And as my movies get longer, I tend to go from G-rated to PG to PG-13. Okay. Okay. Yes.
I think this is what I was asking about. Now that I see this,
Okay.
like the question that was not really. I think this is what I was meaning.
Yes. So you can do this. So you might look at this and say, well, this maybe isn't like a great predictor of a movie rating, right? The ratings versus the run times. And you can probably discern that from looking at the sort of like distribution of the actual data points in here, right? But it is able to pick out some of these general trends in such a way that if you were having to put money on it and guess on a given point in here, it's probably doing still a better job than sort of randomly guessing. And you can test that, right? So how might I determine the overall error of this model?
You could do how many points you actually correctly predicted.
Yeah. So correct, incorrect, right? And so your error rate, would be equal to, you know, the total number of successes divided by the total number of data points. So what if I told you that this model has an error rate of, let's say, 40%? So, sorry, this model has an error rate of Yeah. it has an error rate of 60%, and 40% of the time you're guessing correctly. Okay. So 6 out of 10, every 10 guesses you're wrong. So is this a good model?
Is that context dependent? Because if you're in a field where models having, let's say, a prediction error rate of 60%, the 40% number right, still be useful?
Yeah, so this is, so context really matters here, okay? So you might hear, oh, I'm only guessing 40% of the time, 60% of the time I'm wrong. What is the base error rate of this model?
Like if you guess randomly, you would be wrong 75%.
Yeah, correct. Yeah, assuming that there's like an equal number of movies, but yes, your base error percent would be 75%. So you're doing substantially better, I would say, than randomly guessing, okay? And so there is arguably some value here, yeah.
How do you calculate the base error rate for any model?
So that would be essentially if you were to randomly guess, right? So it's a reference. It's just a reference point against if your model is better than random guessing.
So in code, how would you tell R to calculate that base error rate?
Oh.
Guess randomly and see if you hit the
Yeah.
prediction.
So actually, I would do like a weighted random guess, so not quite totally random. Let's say you have 10%, 30%, 30%, 30%. I would just the number of data points. I would just draw that from a I would like bootstrap it from a distribution where 30% are G, 30% is PG, 30% and 10%. So I would go to this, and then I would pull out of the hat.
10%
You know.
of the time, 30% time.
Yeah, exactly. And I would do that for everything, and then see how many you get right. Yeah.
How do we get 75% error rate? The base error rate?
So assuming that there's 25% of everything.
Oh, I was trying to figure out 75% of 60%.
So if the model, okay, sorry. So
No,
let's say these all have the same number of data points. The model is getting your answer right 40% of the time. If you were just randomly guessing, you would only get it right 25% of the time. You would be getting it wrong 75% of the time because there's 4 outcomes.
Assuming there's equal.
Assuming there's equal number.
And you weight it if there are different numbers.
Yeah. Yes, exactly. So, yeah, this is when you have a logistic model, your boundaries will always be kind of linear like this. Okay? Yes.
So are not showing up because there's no sort of one of these scenarios where
Yeah.
it's emerging as the highest.
Right? Because when we looked at our plots from before, at any given point, you have some probability of having a certain rating, but R-rated movies are never the highest, and so it never gets picked.
That's 75%.
Yeah. Okay, great. Any questions about this? All right, so what we'll do now is look at 2 more two other alternative classification examples approaches outside of MNL.
Can I ask a question?
Oh, yes.
Can we go back to the previous figure?
Oh, not this
The
one.
with the background.
Yeah.
No, just hit the arrow.
Yes. So, because right now the value along x-axis is from 0 to 200.
Mhm.
So, is that true? We interpret to the probability along y-axis as we fix moving runtime to its mean value or not? Because, like when we say along the axis, there's always one chosen category with the probability under a figure, right? Like because there's only one has the highest probability, we choose that one. But if you look at the other direction, there's always 3 categories
Yeah.
together.
So you're saying like this
Yeah. So I would say
versus like this.
yeah, we say that the movie runtime here is fixed to a value instead of random.
If you fix movie runtime based on this plot, I would expect that the highest probability is either always red, always blue, or always almost always green, something like that, right? If you were here, the probabilities would cross, and if you were like somewhere along here, the probabilities would cross, right? And in fact, we see that our average runtime was 88 minutes. So that's like right here, blue, 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 all the way until I get here, and then it changes to green, right?
Yeah.
So if I look at the plot, it should look like that. Here. So I fixed my runtime at 88 minutes, and it's blue, 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 green.
Oh, okay.
Yeah.
Yeah, that makes sense.
Yes.
Yeah, we read this 2 figure differently. Oh, this one is fixed.
Yeah, so this is fixed at 88 minutes. And so, yeah.
Right.
Okay. Let's see if we can get through our next examples. Okay, other classification examples. So the next one we've got is called linear discriminant analysis, LDA. So this is very similar to multinomial, better for well-separated classes. If predictors are normally distributed, then it's more stable than logistic regression. And generally this is more popular when you have more than 2 response classes.
What does more stable mean?
Because the assumptions of the model are closer reflect distributions in the data, the stability, I guess, could be in reference to the accuracy of the standard errors. So typically your errors are going to be tighter.
How much your betas would fluctuate? Is that what it's saying?
Yeah. Yes.
So beta
It's
would-
nuanced, yeah, to the distribution of the data, though. Yeah.
What well separated? It's like discrete. Totally.
So that is something like this, as opposed to so they're more distinct based on your explanatory variables. Okay. I don't know how much I want to get into the theoretical part. Okay, I'm going to write the equations. But this is, again, just for reference. You will probably never have to worry about this unless you're in a more serious machine learning class. I don't think we do LDA much in like econometrics. Okay, so we don't know fk of x. So LDA. So this, okay, sorry, this is the density function of x for an observation from k, and this is the probability of outcome k. Okay, so probability that I have a G-rated movie, PG-rated movie, so on, and this is the density function, or like kind of the distribution of your explanatory variable given a specific outcome. So this is Bayes' theorem, where you're given your response variable already. Okay, but the problem is we don't actually know what the distribution looks like for our x. Yeah.
The difference between pi k and pkx is pk is more of a conditional probability, so probability conditional on some value
Yeah.
of x, and pi k is the overall. Is that the difference between the two?
Yes. So pk of x is probability of an outcome given a value of x. Pi k is just the the total probability. So LDA assumes this. Does this look familiar to anybody? So this describes a normal distribution. So an LDA assumes that the data in your explanatory variables are normally distributed. Okay. And this differs from a logistic regression, which actually assumes something slightly different about the distribution. And this is actually a little bit harder to solve in theory. So it's a little bit, I think, less popular. But generally speaking, the LDA and the logistic regression are going to perform pretty similarly. And the sort of preference for one or the other can be kind of boiled down to some general rules like this, okay? And so if you had to choose, you know, you can do it based off of the separation of the classes and how many sort of response outcomes that you might have. General rule of thumb, okay? So we'll quickly look at that, and then we'll do our last classification example, which I think is a little bit more interesting than the LDA. So yes.
Is there a list, or do you have your own list of, for this type of data, in this use case, use XYZ tests and checks? Because I'm realizing that there's a litany of stuff, and it's, like, when you use it, like, if this is below this number, then you have to check this again and verify this. Like, is that standardized?
No, I think that's very context dependent, and also it's more important to understand like the individual context of each of these models.
Mm-hmm.
And when you are testing stuff, you can run through a bunch of different models and see like which one. At the end of the day, like my preference for MNL versus LDA, it's probably more going to boil down to like which one can give me better outcomes, right? And so I might run the MNL, I might run the LDA and see which one gives me better errors. Okay.
By error, you mean the error rate in prediction?
Yeah.
Okay.
Okay, so LDA, run the model like this. It's pretty similar to a lot of the stuff that we've been doing. You use the LDA function instead of like LM or GLM. So I can run this, and the terms here don't use like coefficients in the sort of traditional sense. These are actually looking at priors in your sort of Bayesian, in your Bayes theorem that it was calculating and solving against. So I actually wouldn't worry too much about trying to derive like traditional coefficients from this. Rather focus on the predictive pieces. So if I were to do repredict based off of the Disney.new, with the LDA, you can put this $class at the end, and what that does is it will classify based off of the highest probability outcomes. Okay. And again, all this code will be available online. Okay, and so what you'll see in this case is a pretty similar graphic, and it's sort of breaking things down in the same pattern. The line or the boundary point might be slightly different, but generally speaking, you can see there's a pretty big similarity between our LDA model, at least in this example, with the MNL. Okay.
Can you compare the error percentage of the two and check which one is better?
Yes, you can. Am I gonna do that right now?
Is
No.
is there a little function to check that
Um,
in a lot of these? So if you're
no, but it's
creating
not that
these-
hard to figure it out, right? You could just put them as columns back into your original data and see which ones
Then,
match, and then have zeros for ones that don't match and ones for that do, and
So there's no inbuilt function to get that error rate. Specify that as an argument in the LDA function.
I don't know, maybe there is, but probably the other way is just as fast.
You want like Amazon Prime of statistics.
Um,
Quick. Okay.
There is one interesting thing to kind of keep in mind here as we think about error rates. You can actually calibrate the model, and we're going to talk about this later on. You can kind of recalibrate the model in ways to try and minimize the error, right? And so, well, that's kind of what's happening here anyways, right? It's trying to your highest likelihood is essentially going to be minimizing your total error. But what happens if I care much more specifically about getting, let's say, G movies correct? What if I care less about getting other things incorrect, right? And so there are things, right? Type 1 errors, type 2 errors, false positives, false negatives. You can recalibrate your model to try and favor ability to predict certain outcomes a lot more, right? And so think about this in the context of like medical outcomes. So if you have like a COVID diagnosis, okay, you can have your total error, which means that the COVID test that I take, it either gives me positive when you are negative for COVID, or it gives you negative when you are positive for COVID. So that's the total error. So you also have false negative error, which is the error related to you actually have COVID, but it tells you you don't. And then you have your false positive, which is you don't have COVID, but it tells you that you do. So the total error is the sum of those two, but which of those two do you care a lot more about?
False negative.
False negative, right? So you can change it so that you care much more about the false negative error and sacrifice your total error, because you're going to be over predicting people who are positive. Your false positive rate goes up, but you're doing that at the benefit of being more accurate about your false negative rate. And so these models where I'm talking about calibrating to your total error in situations where you care about false positives or false negatives, you can actually, change your model in order to try and reduce certain outcomes, okay? So that is one thing to sort of keep in mind as you're conducting any of these models, is what error that you actually care about. So we won't cover specifically how to deal with that right now, but that's a piece of information to keep in mind as I kind of talk about total errors. Yeah.
So just theoretically, you could do that by telling your model that, okay, if you're predicting, let's say you care about getting the PG-13 right, and if you're predicting the PG-13s correctly, it sort of gives you a lower, it's weighted in a way that gives you a lower overall error rate, just because you're predicting the PG-13 points correctly.
Yeah. So it might transform the outcome of this to draw a line like this, and it's like, oh, your total error went way up because you're like mispredicting all of these, but that's okay, because we're getting the green ones, right? Yeah. Okay, so let us talk about the final classification approach. So this one is going to be pretty different. Okay, we're jumping straight into the sort of non-parametric side of things, which is kind of the direction that we're going to be heading in our modeling in the near future anyways. But we're going to do that starting with a technique called K nearest neighbors. Okay, so I'm sure some of you guys have probably heard of this before. I'm going to write the equation just for reference. So this is the technical equation for K nearest neighbors. So what the heck is going on here? Actually, this is a very straightforward algorithm, so I would not even worry about the math, okay? So essentially what this is saying is, given a positive integer k and test observation xo, identify the k points closest to xo represented by no, estimate probability for class J as the fraction of points in NO whose response equals J, classifies XO to class with largest probability. Okay. What? Okay, let's do this. Let's do a simple example. And hopefully this will be much easier to interpret. Actually, let me... All right, we're going to have a bunch of points here, and we're going to have a bunch of points here. So our data looks something like this, and I will put a single point right here. So at k equals 1 is our dot equal to that or that? What do you guys think?
Red.
Red. Okay. So k nearest neighbors, I'm going to look at my one. I'm going to only look at one nearest neighbor. And so that's red. So this guy is red. Okay, what about at k equals 2?
Still red.
Yeah, that's right. So my two nearest neighbors are here and probably here. And so it'll just retain the one from before. What if my point was over here? My two nearest neighbors are blue, so it'll be a blue X. Okay? And at 3, maybe my 3 closest points are these 3, so then that would be red. My 4 closest points are maybe this, and this, so this will still be red, and so on and so forth. How many points are there? 5, 10, 12, 17, 19. Okay. All right. So here, K nearest neighbors 1. What would this be? How about 3? Blue 5. Still blue. What about 19? It would be red, right? Because I'm going to look at every single point here. There's more red points than blue points, so this becomes red. Okay? That's it. That's K nearest neighbors. It's pretty easy. Yeah.
When K was 2 and the point was sort of in the middle,
Yeah.
then K was red based on its proximity to the red point?
No, actually, I think it's based on the last one, on the previous number of K nearest neighbors.
So if K was 1 and because the answer was red,
Yes.
since K2 was a tie because the nearest point
Yes.
was a blue one and a red one, it's based on
Yes.
the previous one.
Which is the same thing as what you were saying, actually. It's also based on distance, right?
Okay. Yeah.
Pretty straightforward. Yes.
So you would use this when you already have a set of data that you have. So you have your testing set, training set. Or maybe you already have data and then you have new data and you need to classify it and you don't know anything about it. So it's like just dumped on you. Or is it for like how?
It's this, right? Well, K equals 3. What would this point be? Blue. 1, 2, and something. Doesn't matter. These are both two blue and 1 of whatever else. Okay. Right here, K equals 5. What would that be? Red. 1, 2, 3, 4 red, 1 purple, red. Great. So,
So I just want to clarify.
Yes.
Did you say we assign the last closest points to the one we are looking for, right? Or the one of interest? Then, but you also count the number of the right dots over there. So it seems like the first statement seems like doesn't count the weights, but the second statement seems like it counts the weights.
what? Wait. It's just, you just count how many points are close nearby.
Did you also mention it only counts the value of the last closest?
No, so, okay. I'm gonna use my mouse here. So, there. Okay. Okay, so let's say the point is right there. So first nearest neighbor, this point would be what?
Green.
Green. Okay. K equals 2. You have, let's say these 2 points are the closest points.
Right.
So at K equals 2, you have a tie.
Right.
You have green and blue. So what should it be?
The closest one?
Yes. It's technically, yes, it's the closest one. It's the previous value, which is the closest one.
Right.
It's just based off the closest one. So if it's green, if K equals 1, then it'll also be green at K equals 2, even though it's tied.
Oh, okay.
Yeah?
Yeah.
Make sense? Okay, cool.
When you do that point like there, you say K equals 3.
Yes.
So we know that K equals 1, it's green, but when you get to K equals 3, then it might be blue, right? And then you classify it as blue even though it's green.
sorry, what?
So where your mouse was previously the example that you just
Yeah.
did, and you said k equals 1, the mouse would be green, right?
Yes.
K equals 2, the mouse is still green.
Yes.
But then when you do k equals 3, you actually get 2 blues and a green.
Then it would become blue.
Then it would become blue, even though.
And so
No, it's
you have to
green.
define
Yeah.
K though.
Yes, you
Up
have to
us
define K.
K.
How do you choose K?
A test. Did you make it up? Visual?
Context.
Minimize the error. How do we do that? Cross validation.
Okay.
Same thing that we've been doing all along. Yeah, so you can actually base your K on the one that gives the best predictions, right? So out of sample test predictions, blah, blah, blah. You know the drill. Okay, cool. So, dang it, I forgot. Okay, so I need to do a correction here that I forgot to do last year, and so, okay, so there's a small problem here, specific to this problem, but as a generalization. So my k nearest neighbors should be based on Euclidean distance, right? How close I am relative in any direction. So what is the problem?
That when the k equals 3, when you count 3, and the point of interest close to the green, and then you count 2 below after assign 2 below, that doesn't really account for Euclidean distance.
No.
That I might have to make decision, but
No, not quite. So it doesn't matter how many k's there are. You can always still calculate a Euclidean distance. Specific to this example, what is the problem? Yeah.
The scale of
Yes.
that versus.
Yeah, exactly. So really, right, the scale is like 0 to 200. So if I were doing Euclidean distances, then this plot would look like, this plot would look like this, right? Because the scale of my runtime and the scale of my rating is different. So I have to normalize the data. Yeah.
Do it similar to the classes we did, 1 to 5 and 1 to 5.
Yeah, I mean, you have to normalize it in some way, and I did not do that in my example code, so we're gonna make this up on the spot. Okay, Disney dot normalized. Okay, Disney dot filtered. So I need runtime and rating to be normalized. Okay, how do I do this again? 1 second. Actually, I have a. Didn't I normalize something in another lecture? Does anyone remember which one I did that in? It was in the Ridge and Lasso regression lecture, which was lecture 9. All right. Or did I? All right, 1 second. Scale. Okay, we can use the function called scale to do it. All right. This is what happens when you put me on the spot for coding. Scale runtime min. And rating. Okay, so let's run these guys and take a quick look. Okay, great. So these are normalized and ratings are normalized. Perfect. Okay, so now I am going to copy and paste some code. Okay, example, k nearest neighbors. We'll do this again. You're gonna have some training set, testing set, and the training set is our original data, and then I'm just asking it to predict over that full range. So we're not doing the whole cross-validation or anything. I'm just doing that range across rating and runtime like before. Here, I'm gonna generically choose 3 neighbors. Okay. I need to change filter to normalized. And our outcome is what the CL is referring to. So we'll run this. Oops. Whoa. It's probably because.
Still Disney
Yeah.
flavor.
Here we go. Please work. No. Oh.
Is Disney new, not skip?
Yeah. Okay. That's why. Okay, hang on. So we need to do a different Disney new. And we're going to sequence from Disney.normalize min of Disney.normalize dollar runtime to the max one. Max Disney.normalized dollar runtime min by, let's say, 0.01. And then rating Disney.normalize $rating to max Disney dot normalize $rating. Okay. Oops. There we go. Oh. I saw it for a second. There we go. No. Oh. Is it just taking a long time to process? Is that why? There it is.
Oh my gosh.
Okay.
It's art.
Cool.
This is the kind of stuff they haven't made modern.
So actually,
This is quite beautiful.
like a very simple approach, and you can see it can do all these like weird nonlinearities and stuff like that, right? And we'll actually see how this can change as we change the K's. So we'll wrap up next time. I don't want to go too much longer, but you can see actually a very simple approach can give you these really non-linear functional answers compared to like the logistic and LDA that we were doing. Yeah, so we'll wrap up our KNN next time.
What was your K number for
3. Yep. And as your K's grow in number, I can show you guys real quick. Like, let's set K equal to 50. You can think about what happens here as you pack up and yeah, and so these start to converge, and actually you can imagine if I have K equals the number of data points, what would the prediction be?
It would look exactly the same. It would look close to what we have before, right?
No.
Just one color.
It'll be one color. It will be whichever data point is the most prominent, right? Which I think is probably blue.
I think we start an artist collective where it's abstract line art based on collections. I think we do pretty well. There you go.